Thank you. Hello, everybody. Thank you for the introduction, Leslie, and also thank you to the organising committee for inviting me to give a plenary talk today. And I'm going to talk about the challenges within the oil and gas industry, looking at the accountability of various mercury sources. Next slide, please. So mercury is naturally occurring in the reservoir, and it can be distributed between the gas, the oil and the water phases. And after the mercury is extracted from the well, the mercury becomes distributed in those three phases. And you'll see from this slide that the concentration is actually quite variable. These numbers are from the literature and also from doing personal measurements in the field. So we've got gas at 0.05 to 5,000 micrograms per cubic meter, oil at 0.1 to 20,000 ppb, and water from 0.1 to 5,000. The reason that these concentrations are so variable is because the geology in the well dictates the mercury concentration, and it's different all around the world and also on different wells. During the extraction, of course, we also get some solid waste generated, such as drilling muds and sludge, and also some atmospheric emissions from flaring vents and various exhausts within the process. Next slide, please. So it's well known and accepted there are mercury hotspots for oil and gas around the world, and this map basically summarises where those are. And these coincide with the geological mercury belts. Most of the work that we have done has been in Asia and Northern Europe and also South America, which is where the hotspots of mercury are. Now, the other thing to mention is that there's a general trend in that the deeper the well and the hotter the well and the sweeter the well, the mercury concentration tends to be higher. And as we explore new fields, we're likely to, in the future, get more fields which are high in mercury. Next slide, please. So the oil and gas industry have been dealing with mercury problems really over the last 30 years. I think at the start, they were a little bit in denial about the amount of mercury they might have in their process. But these days, I think they are the mercury is well managed, and there's a good understanding within the industry, but there's still a lot to learn. So the main thing to realise is that most of the measurements for mercury and gas are done to protect the process equipment. So as mercury flows through a gas plant, for example, it has to go through some cryogenic heat exchangers, which are at a low temperature. And even at low concentrations, this mercury can pre-concentrate and build up, and it can, in some instances, lead to a cold box failure. Mercury can also poison the catalysts which are used in the refining process. This can lead to plant shutdown, an interruption of supply, and financial losses. And in a couple of cases, there has been explosions due to the failure of cold box components. So there's obviously a hazard involved in that as well. Also, all of the gas products and oil products that this industry generates are exported with quite tight specifications. And if these specifications are not met, then the products are either rejected or they have to sell them at a reduced revenue. So there's some commercial reasons why people want low-level mercury in these streams. There's environmental issues, there's contamination and decontamination issues. This is particularly a problem when you're decommissioning your plant, because mercury will collect in all of the pipeline and all the vessels. You can also deal with contaminated solvents, emulsives, and this in turn can lead to some occupational health and exposure issues, because a lot of the maintenance crew and operators have to, maintain the plant and deal with these contaminated equipment. The sludge from the oil and gas industry is actually very high in mercury, and it tends to accumulate in there. And this also creates a problem in terms of storage and processing and disposal. And finally, there's mercury in the wastewater streams, which has to be removed before discharge, and that is obviously another operational expense. Next slide, please. So the problems of mercury really begin at the well. And this slide really shows a separator, which separates the oil, the water and the gas as it comes from the wellhead. The thing to notice about this slide is that the temperature in the well is actually hotter than the separator. And so during the extraction, what can happen if the concentration is high, the mercury in the well as it's extracted can start condensing as small mercury droplets. And then that, as it goes into the separator, can fall out due to gravity and get attracted to sludge and waxes. And then that will go into the water phase as ionic mercury and elemental mercury. And it can also go into the oil as the sludge and the elemental and dissolved forms. The volatile elemental mercury from this process actually goes to the gas phase. So it's a complex operation which is different on every site, and it also depends on the process conditions and the concentration of mercury in the well in the first place. And so this really is an important slide, because what I'll talk about later is that the importance of measuring at this location so we can look at the true levels of mercury that are generated from this industry. Next slide, please. So I'd now like to show a very short video clip of elemental mercury condensing on an offshore platform. Can you push start, please? So what you can see here is pure elemental mercury condensing from the process, and this can build up over a period of time. I've been on sites where they have to release this mercury and decant it off almost on a weekly basis. And this is really one of the unaccounted emissions of mercury on these gas plants. This typically only happens when the concentrations are high, but there are places in the world that have to deal with this problem. Next slide, please. This is a photograph of some maintenance guys on a petrochemical plant that are emptying the elemental mercury that's been collected in this section of pipe. Next slide, please. You can actually explain this process by looking at the vapor pressure curves and relating the concentration of mercury that we measure to a process concentration. That's one of the people, most people actually forget that the process concentration is actually highly concentrated, because if you take gas at 1 microgram per meter cube, for example, that's your measured concentration, and it's in a process which is at 50 bar, the actual concentration in the process would be 50 micrograms per meter cubed. What this graph shows is that it shows the process concentration against temperature. And you can see on here the red line, which is in the gas phase mercury. When you get to about minus 30 degrees at these conditions, you'll start condensing liquid mercury. And next slide, please. If you increase the concentration, the mercury condensation occurs earlier at a hotter part. So that's 10 micrograms minus 10 degrees. Next slide, please. At 100 micrograms per meter cubed, it'll start condensing at about 12 degrees. Next slide, please. That's 1,000 micrograms per meter cubed. You'll start condensing at about 38 degrees. So if the concentration is high, there's a temperature drop at the wellhead, you will get mercury condensation. But this condensation can also occur anywhere in the process if you reach saturation conditions. And that is one of the reasons why you get cold box failures. Next slide, please. So during the extraction, you also generate a lot of produce water and drilling fluids. And of course, the refining of crude oil generates a lot of wastewater. The approximately 250 million barrels per day of water is generated by the industry. And this quantity increases with age and production rates. Now, some of this water gets re-injected back into the well, and some of it is discharged. So the exact ratios of what is discharged, and I couldn't find this information, but this is the estimate that I've taken a stab at. Now, The concentration, as I mentioned at the beginning, for produce water is extremely variable. We've seen concentrations between 1.1 ppb and 5 ppm. The discharge limits for the industry vary around the world, and we've seen discharges of less than 0.1 ppb as high as 100 ppb. So the other thing to realise about mercury in the produce water, it's normally associated with particulate material and sludge. So if you filter the produce water, which is a requirement because you have to remove any oil and dissolves and solids before discharge, then that filtration system will collect mercury. I think overall, I would say the discharges are well regulated, and overall the emission to the environment is probably low from this, but the volumes are very high. Of course, the wastewater streams from refining operations are also quite complex, and we have different processes which are known to have high levels of mercury. Next slide, please. So in order to estimate the annual discharge, what I've done is I've taken 5 different concentrations which we've encountered, and I've then applied that to the discharge rates on an annual basis to calculate the tonnes per year that we might expect. So if we're down at the 0.1 microgram per metre cube, just looking at the 40% discharge into the sea, we're probably around 0.6 tonnes per year. But that's not really what I'm trying to, but I think what we have to consider here is actually the amount of mercury that's generated from the process, which has to be treated. In this case, you could have several hundred or even maybe thousands of tonnes of mercury, which has to be removed by the water treatment. So the fate of this mercury is, needs to be considered. And also in this slide, I put some concentration ranges that we've encountered from our work in the field. Next slide, please. So I've got 2 case studies I'd like to mention. The first one is an offshore platform in the Mediterranean Sea. This produces gas and crude and also about 4,200 barrels per day of produce water. The inlet concentration at this site was measured to be 320 ppb and the discharge about 0.05. We know from this site that the filtration process removes nearly all of this mercury, but it still means that the site generates about 100 kilograms of mercury per year, which is collected in the treatment process. And the fate and the disposal mechanisms of these filtration systems is not really known or documented to my knowledge. Another example case study is in South China Sea. This is some work by Darrell Gullop. And again, they have about 20,000 barrels per day of produce water, high concentrations. But in this case, they decided to inject the produce water back into the well. But before they do that, they still have to filter and clean the water. And that could equate to about 230 kilos per year. So this is just 2 sites. And I'd like you to bear in mind that there's actually 12,000 offshore platforms worldwide. So even if this concentration is low, this is still a significant amount of mercury. Next slide, please. So during the extraction, drilling fluids are used, and it's quite well known that the water-based drilling fluids, which contain barite as a weighting agent, contain some mercury. So we took 10 commercial barites, we tested them for total mercury content, and we found an average of 22 part per million. This was a little bit higher than we expected because the US specification for dry barite is around 1 ppm. So if you look at the annual discharges of drilling fluids, that equates to about 0.5 tonnes of mercury. If you use the US specification, about 11 tonnes of mercury per year if you use the PSA mean that we found. I couldn't find much information about drilling discharges onshore, but the amount of discharge is much higher. It's 53 million tonnes. So I think it's very difficult to establish the amount of mercury that's coming from these drilling fluids, but again, it could be quite significant. And it's believed that the mercury is in the form of mercury sulfide, so arguably it's not bioavailable. Next slide, please. So now coming on to crude and condensates. We've already mentioned there's a very wide concentration range, but speciation is more complex, which means it's more difficult to predict how the mercury will behave during the refining process. We do know that certain processes like desalting and caustic wash treatments would remove mercury. And we also know that when you stabilize a crude, which means you get rid of the gaseous components, the elemental fraction that's dissolved in that crude is released to the overheads. It's also well known and accepted that during processing, the mercury tends to pre-concentrate in the lighter fractions, it also gets lost in the actual refining process in all of the pipework and all the vessels and collects in the sludge. So it's extremely difficult to do mass balances on these type of facilities. Mercury cleanup is used, but predominantly mainly for the lighter products and the refined products. And there are some quite tight specifications that the industry has to meet. But the heavier streams like diesel, kerosene, fuel oils, you know, are not actually normally cleaned up for mercury. And so there's a lot of these fuels that actually are combusted on various processes, and they haven't really had their mercury removed. So that again is potentially quite a large emission due to gas emissions. Next slide, please. So what I did is I took the annual crude production per year in tonnes per year for different regions. Then I reviewed the literature, and from there, there's a few papers which assign average values for each region. This is very speculative and it depends on what paper you read. There's a good paper by Mark Willem. There's some nice data that QA3 have presented. This is another testing company that are based in the UK, specialising in the oil and gas industry. We have our own data, and also there's an IP, ICA and unit reports. And when you apply those numbers to the annual production rates, you can see that there's a big discrepancy on what people believe is being emitted, between almost 6 tonnes a year to 170 tonnes a year, depending on which data sets you take. Next slide, please. We do know that during the refining process, mercury does go into all of the products. And as mentioned previously, the mercury in these feedstock tends to up into the lighter fractions. And even if that what we found is that even if these feeds contain some particulate mercury, a lot of that particulate mercury is mercury absorbed to particles. And then, of course, during the distillation process, this heats up these particles and the mercury gets released to the lighter fractions. If there's cinnabar in the sample or mercury sulfide, then this would tend to go to the residue and go through the vacuum distillation process to the petroleum coke. Another confusing part about mass balances is that very often when you measure the streams from the refinery, they can be at a higher concentration than the feed, and that's because this mercury pre-concentrates in those streams. So you have to look at the mass flow rather than the concentration flow. Next slide, please. So I'm now moving on to gases. So we've already talked about what can happen in the gas well, when mercury can get condensed when you remove the condensate and the water. So the gases have to be purified before they go to the fractionation plant. And these processes can also remove mercury, and that's not very well characterized. So you have acid gas removal, which removes H2S and CO2. This typically uses something like an amine solvent, but when you regenerate the solvent, you heat up the solvent to release the gases, and the mercury can also come off. That would go into the sulfur recovery unit, so it can go to the elemental sulfur, or it could go to the tail gas, which then gets incinerated, or it just emits to the environment via a flare. Downstream with the acid removal, you normally have dehydration to remove the water, so you don't get hydrate formation in the process later on. And that also removes quite a lot of the mercury. Glycol beds are typically used, and they collect the mercury, and then during the regeneration of that glycol, they're heated up and the mercury is driven off, and then that also goes to atmospheric vents. Mercury removal on gas plants is very well established and actually very efficient, and it needs to be, because the concentration that you need to get down to protect the cold box is around 10 nanograms per meter cubed. And our experience is that these mercury removal units work extremely well in the field. So most of the mercury from the gas actually goes onto the mercury removal adsorbent. You can also get some mercury losses during the nitrogen rejection and also in the fractionation train, because you're dealing with very low temperatures and very high flows. So even if the concentration is low, it will still collect in this process. So it's just about managing this mercury that is not removed. And then of course you get mercury in the products, which have to meet the specification. Next slide, please. And again, the complication is that this mercury will collect in the process in all of the pipe work, so it's very difficult to do a mass balance. Next slide, please. So I've done the same with the gas as I did for the condensates. I've taken the gas production rate in meter cube per year for each region. And then I've hypothetically assigned a concentration to that we would expect for an average concentration, ranging from 0.01 microgram per meter cube, which is the specification limit for most sales gas, up to 1,000 micrograms per meter, which is a real extreme, but it's not impossible to get these levels. And you can see here that there's the potential for a lot of mercury generated from the process and hopefully collected by the adsorbent material, but some of this will be emitted due to the processing of the gas. I've also taken some data that QA3 presented and some of our own personal data, which also includes a review of the literature. And my best estimate is that the upstream generation of mercury is around 147 to 230 tonnes per year. It's also worth noting that about 3% of this gas is flared. And so whatever number you want to take from these tables, that could amount to an appreciable amount of gas. Flaring normally occurs upstream rather than downstream on the products. So I would say it would be the higher levels that are being flared. And UNEP have obviously published some good reports on this topic. And I noticed in one of their reports, they said that they contacted mercury recycling companies. And in the year 2015, they claimed that they collected between 330 to 100 tonnes of mercury from the industry. But if you look at the numbers I've presented in this table, there could be quite a difference between what is being recycled and what is being generated. Next slide, please. So this is just an example of one gas plant that we've worked on over a period of many years. This is the gas plant in Croatia, where we know that the mercury concentrations can be high because of the geology. And the boxes in red actually give the yearly averages that have been measured. So the inlet to the mercury removal is about 516 micrograms per meter cubed. The outlet was 0.2 micrograms. There's some mercury removed, as we expect in the amine and the molecular sieve dryers, down to 0.018 micrograms per meter cubed. Then the outlet concentration is less than 10 nanograms per meter cubed, which is what is desired for the cold box. However, if you take the production rates for this plant, which is about 0.8 billion cubic meters per year, that's equivalent to more than 400 kilos of mercury from one gas plant. Next slide, please. So if you delve a bit deeper into the process, you'll realise that there are some sources of unconsidered mercury emissions from the process. And QA3 actually did produce a good report, and they're speaking at this conference on this topic. I've covered most of these, so I'm not going to go over them again, but there's a few there that people don't really consider. That's such as the atmospheric venting from actual storage tanks. There's quite a lot of work going on with decommissioning, and the sludges and the debris from the pipelines that people are encountering are extremely concentrated in percentage levels of mercury. And so the industry actually generates quite a lot of waste products. So it'd be quite interesting and to get a better understanding of how these are processed and dealt with. Next slide, please. So Leslie actually asked me to cover 4 questions. The first one was, what is the major issue and problem in this area? And I would say it's really the current mercury inventory. I don't think is truly accurate and it's not fully understood. So I think a lot of the mercury data that is used is based on more exported products. And it doesn't really reflect on how much is generated during the processing and the extraction. The next question was, what are the potential solutions to this problem? I would actually like to see more data reported, and maybe it'd be nice if it was mandatory, to report the levels in the oil and the gas and the water right at the point of extraction, so at the primary separator, because we know the metering rates here. And if we could get a good, accurate number from how much is in these streams before processing, we'd have a better characterization, accountability of how much waste and mercury is actually being generated. Why has the problem not been solved yet? Well, I'd say there's no real incentive to do the measurements here. It's actually difficult to do the measurements there as well. Most of the measurements that are conducted are all about testing the efficiency of the removal system and also on the products to make sure they meet specification. And every now and again, there's a study done on inlet concentrations, but it's not a routine testing. So if we could wish for 3 things to solve the issue, I would say we need more research on the fate and transport of mercury during oil and gas production. There are some publications, but I don't think it's the true story of what we see. I think you need more development of mercury removal for liquid phases, crude oil and condensates. And also I think the sampling techniques and some of the measurement techniques that are being applied for the industry are a little bit suspect. And so really in the lab, you can only analyze what you're given in terms, and I think the measurement is good in that case, but really a lot of times we're analysing a sample that's not representative of the process or the bulk flow. So that problem has to be dealt with as well. So my final slide is I've tried to take all the information I've gathered over the last few months and put it into a conclusions table. And there's 2 sections to this table. There's the mercury that is generated from the process, from various components, and also from the processing of the gas and the oil. And there's also what I believe is to be the emitted amount, which is the uncontrolled emissions to the environment. You can also see from this table, there's a lot of question marks because I couldn't really come up with a number on what these are. And of course, there's such a wide concentration in the feedstocks, it's really difficult to just generalize and come up with numbers. So my best estimate, the emitted mercury is between 10 and 62 tonnes. But the amount generated is closer to 400 or maybe even high as 5,000 tonnes per year. But of course, that is managed and collected within the process and actually on the absorbent systems. So it's difficult to predict, to really get a handle on how much is being generated and what the associated emissions are. I think some of the data I've shown, and maybe some of the data from QA3 might be biased high, because we normally get involved when plants have issues with mercury. And of course, there is a emission to the atmosphere due to flaring and combustion, and there's an emission to the water that has to be considered as well. Okay, I'm sorry I've gone over the time, but it was hard to get all the information across in the time that I had. Thank you.
Thank you, Warren. There's, as they say, can open, worms everywhere. It's interesting to see that we might not know as much about this sector as we think we do, and there may be more of a problem than we're aware of, and something certainly that UNEP should focus on in future to make sure that the global inventory is correct and that we have a full cradle to grave understanding of where mercury is going in the environment.
Yes.
So one question that's come in: how accurate are these measurements? You're talking about very low concentrations and trying to do mass balances. How accurate are the measurements, and how easy is it to go through the sampling and measurement process?
I think you have to treat the gases, the water, and the oil, and the crude and the condensates differently because they have different issues. In a lot of cases, when we're sampling water, especially inlet measurements, it's difficult because you have a condensate, a water material, which has got oil and suspended particles. And so if the lab filters the sample, they're going to get low results. Also, these streams contain elemental mercury. And so by the time you've collected the sample into a bottle and sent it to a lab, you're likely to have some mercury losses. Most of these measurements are done onshore. There's also an observation that the mercury actually gets stuck in the boundaries between the oil and the water. And so if you're taking a sample and you actually measure those boundaries between the phases, you would typically get a much higher result. In the case of gas, I think the measurements and the sampling is fairly accurate, but you have to have very high bypass flows, and actually it's actually quite time consuming to precondition the sample point. And a lot of contract companies really don't have the time or the luxury, so they just quickly take a quick sample. And so I think there's a little bit of that going on in the industry, whereas if they took the sample for longer, flushed the lines, they would get a more representative result. And for condensates, I think this is a very difficult measurement to take. And if you try and do an interlaboratory comparison of raw condensates between labs, you get a very wide range of numbers because the sample's not homogeneous. It gets associated with all the particulates. Measurement systems measure different amounts of particulates. When you collect the sample, which is at high pressure, you depressurize, and that off-gasses a lot of the mercury as well. So I think sampling is key to getting accurate results, and I think more work needs to be done on that.
Thank you. We have another question that's coming via the chat from Vernon. In a previous talk yesterday, he learned that time scale accumulation in the pipelines from the wells under the sea. So is there mercury accumulating at scale in the marine environment under the sea in these pipelines? And is there any risk of this getting into the marine environment?
Well, I think it's a closed system, and it does accumulate on the pipelines. And you can see this when you first start working on a new rig. The levels going onshore are sometimes maybe only 1 or 5% of the actual concentration you measure offshore. That builds up for a period of time. And we have quite a few online instruments that do online measurements onshore and offshore. And you can see that this amount of mercury that's being exported changes after they've pigged the line, for example, which is a process where they're removing all of the debris in the pipe scale. So it's changing with time and it's evolving. But the mercury on this pipeline is actually quite difficult to remove. It's normally there in the form of cinnabar, and because it's a closed system, I wouldn't expect it to be releasing mercury into the marine environment. But of course, when you deal with decommissioning, you have to make a decision whether or not that pipeline stays there indefinitely or whether or not it's removed. And that would be the time when there could be some environmental issues that have to be considered.
Excellent, thank you. So it's not a concern specifically, that's the relief. Okay, thank you, Warren, very much appreciated. And I suspect more questions will come into this, and it's certainly something we need to investigate more at the UN level. Moving on.